lecture series of CMOS by KT Semicon. So in previous video, we'll discuss the things related to MOSFET, right? How MOSFET is having operating condition, what is meant by MOSFET, and how a MOSFET is constructed, and all, and related to NMOS, CMOS, NMOS, and PMOS, all these things, right? So in today's lecture, we will discuss the things related to operating conditions, as we are having some cases in MOS capacitor, right? So here also you are having four different regions of operations. So in this MOSFET, we'll saw the things related to enhancement MOSFET and depletion type MOSFET, right? So in enhancement MOSFET, there is no channel in between source and drain. If there is no channel, means there is no connecting path in between source and drain in enhancement type MOSFET. In that case, we are applying the gate voltage as 0, right? So after that, we are having depletion type MOSFET. So in depletion type MOSFET, we are applying the gate voltage as more than my threshold voltage. Then what happened? There is a formation of inversion channel in between my source and drain. So whenever we are applying the drain voltage, so we are having different kinds of operating conditions. Okay, let's see what are those. Okay, so let me share my screen. One minute. Okay, I hope my screen is visible, right? So up to now, we'll see what is meant by MOS structure and NMOS, PMOS, and how a MOSFET is basic MOSFET, and we are having two different types of MOS transistors: enhancement type MOS transistor and depletion type MOS transistor. In enhancement MOS transistor, there is no conducting channel, right? So in depletion type MOSFET, we can observe some C. So whenever we are applying the gate voltage is more than my threshold voltage, then we can see the conducting path in between the source and drain, right? So whenever we are applying this voltage, gate voltage, then we can see one conducting path in between my source, and again we are applying the voltage at the drain VT voltage, then we can see what are the operating conditions and all. Okay, in depletion type MOS transistor. Okay, this is one basic NMOS transistor. I just want to construct a NMOS transistor, right? That's why I'll select here P type substrate. Okay, so here we are having one terminal as source with pentavalent impurities, right? Because I just want to make NMOS transistor. That's why I doped with pentavalent impurities. So here we are having gate, and this is my metal oxide, and this is my substrate. Okay, three different layers: gate, oxide, and substrate. Okay, so after that we are having another terminal as drain. Okay, so in between that we are having one channel region. Okay, so already channel is created whenever we are applying the gate voltage is more than my threshold voltage, then there is a formation of channel in between the source and drain. Okay, and we are having another terminal also here, like bulk terminal. Okay, this is the basic structure of a NMOS transistor. Okay, so after that, some of the key points, okay, related to MOSFET. So in enhancement MOSFET, channel formation is required for the conduction of current in between the source and the drain. So what is the meaning of this point? So in enhancement MOSFET, we don't have any channel in between the source and drain, right? Okay, if I want to conduct a current, then we need to create a channel, right? So here we need to require the channel formation where in enhancement MOSFET. Why? Because before that we are not having any channel in between my source and drain. That's why if I want to conducting path, conduction of current in between source and drain, then we need to make a channel. Okay, so this is the enhancement MOSFET. And in depletion MOSFET, what happening here? So already channel is created in between the source and drain. We are having already a conducting channel. Okay, in depletion MOSFET, now what we need to do, we just want to control the current. Okay, so whenever we are applying the VD voltage at the drain terminal, then my conduction is increasing. Why? Because already we are having one conducting channel in between my source and drain. That's why what is required here, we need to bias. Okay, we need to bias it. Biasing is required to stop the current, right? Okay, so we need to biasing the current to, we need to, here biasing is required mainly. Why? Because already channel is inbuilt is created in depletion time. Okay, so gate bias voltage controls the current condition of MOSFET, right? So here depending on the gate voltage, okay, and my VD voltage, okay, we are controlling this current condition, right? So that's why MOSFETs are voltage control devices. Okay, depending on the VD voltage and VG voltage, we are controlling the devices. Okay, so we are controlling the MOSFET. That's why it is known as current control device. Okay, so after that, we are having four different regions. MOSFET operations is divided into different regions based on the voltage applied at the gate terminal and the drain terminal. Okay, so this is the thing here. So we are having four different types of regions. First one is gate cutoff region. So in cutoff region, so remember, my gate voltage is more than my VT. So this is fixed voltage at the gate. Okay. So whenever we are observing the MOSFET operating conditions, okay, this is for depletion type MOSFET, right? So in depletion type MOSFET, already channel is created. Why? Because we are having the voltage. My voltage is more than my threshold voltage, right? So this voltage is fixed. We just want to change the drain voltage. Okay, depending on the changes in drain voltage, we can observe the four regions, right? So first one is cutoff region. How cutoff region is formed? Whenever we are applying the VD voltage as 0. Okay, so my channel is there because my, this is the gate voltage, my channel is there, but my VD voltage is 0. We are not giving any voltage at the drain. What happened? Even though channel is there, but there is no operations, there is no conduction of current because my drain voltage is 0. Okay, so coming to linear region, so whenever we are increasing the VD voltage more than my 0, which means some small amount of VD voltage. Okay, here we are applying the positive voltage in a small manner. Okay, so whenever we are increasing the VD voltage, then my ID also increases, starts increasing linearly. Okay, that's why it is known as linear region. After that, we are having threshold of linear region, which means pinch off region. Okay, and after that we can see one saturation region. Here my ID current is saturated. Even though we are increasing the, my, even though we are increasing the VD voltage, my ID current is constant. Okay, I'll explain how this happens and all. Okay, so first one is cutoff region. See here, in cutoff region we are having three layers, right? Metal, oxide and substrate. Okay, and terminals are source, gate and drain. Okay, here bulk is also there. Okay, so in this case my gate voltage is more than my threshold voltage. Because of that reason, we are having already one inversion layer, we are having one channel in between the source and drain, but there is no conduction. Why? Because there is no conduction of current, means here we are applying the drain voltage is connected to ground. Okay, so whenever we are applying the drain voltage is 0, so here my drain voltage is 0, even though I'm having one conducting channel in between the source and drain. So because of this VD voltage, there is no conduction of current in between the source and drain, right? That's why we can see one cutoff region here, right? So this is the condition, my gate voltage is always more than my threshold voltage, then one inversion layer is formed in between source and drain. That layer is known as inversion layer, right? So this is the inversion layer, and depletion layer is present but no carrier flow. Why? Because my VD voltage is 0, right? At this case my transistor is completely off. Okay, so that is the reason this is known as cutoff region. Why? Because my transistor is completely in off condition, even though channel is there but there is no drain voltage, right? So this is the cutoff region. After that, linear region. Okay, so in this, 1 minute. Okay, sorry for the delay. So now we can see one linear region. So what happening in linear region? So we are having inversion layer same as the cutoff region. But what is happening here? In this case, we are connecting the drain to ground, which means zero voltage. But here we are applying some VDE, small amount of VD voltage. Then what happened? Whenever we are applying the small amount of VD voltage, then we can see that there is one conducting path. Why? Because whenever we are applying the VD voltage is more than zero, then the electrons is moving from source to drain. Whenever my electrons is starts moving, then we can see one ID current flow. There is a conduction of ID, but this ID current is in linear. Okay. Why? Because we are applying the very small amount of VD voltage, right? Because of this small amount of VD voltage, my ID current is increases linearly, not more current. It is increases linearly. Okay. So here my gate voltage is same more than my threshold voltage, and oh, so sorry for the delay. Okay, so let's continue the session. Okay, so here whenever we are applying the gate voltage is same more than my threshold voltage, and we can observe some VD is in the form of small amount of VD voltage. Then continuous inversion layer is connection. There is a one connection in between source and drain, right? So we are having one conducting channel, and there is a one electrons movement is also there in between source and drain. That's why we are having some ID current. Okay, transistor acts as a voltage controlled resistor, which means whenever we are applying the voltage, then only it starts working, right? So this is the condition, and drain current is increases linearly with VD. Okay, it increases with VD. VD is small. Whenever we are applying the small amount of VG, then my ID current is increasing linearly. Okay, so this is the case, and here we are connecting the substrate to zero. Okay, so again we are having the threshold of linear region. So here we are increasing the VD voltage is more than my threshold voltage. Okay. Okay, so what is happening here means, so whenever we are applying the large amount of VD, which means we are increasing the, okay, so we are increasing the VD voltage. Okay, so whenever we are starts increasing the VD voltage, then what is happening? So my channel is trying to pinch it off. Okay, so as compared to source side, my drain side, my channel is pinched off. Why? Because we are increasing the drain voltage. Here in this case we are having only small amount of VD voltage. Okay, depending on the voltage my electron starts moving, and there is a connection of ID in linear case. But in this case we are increasing the VD voltage. Whenever we are increasing the VD voltage, then what happening here? So my channel is pinched off at it decreases, and but at one point there is small amount of connection in between source and drain. Okay, so in this case, that's why it is known as threshold of linear region or else pinch off region. Okay, so here I'll mention or not. Okay, here we go. Pinch off it is known as pinch off region also, right? So condition is this one, not VD saturation. We are increasing the VD voltage is more than my V threshold. Okay. So exact boundary point between linear and saturation region. So in this case, we can see some linear currents. Okay. So after that, in saturation region, we can see some saturation currents, right? But in this case, we can see some pinch off, which means boundary point, exact boundary point, right? So still continuous, but starting to narrow at the drain. There is a connection in between source and drain, but it is very narrow, very small amount, very exact boundary point. Okay, so this is the case. This region is known as pinch off region. Okay, so again we are increasing the VD voltage. Okay, in this case, compared to this case, again we are increasing the more amount of VD. Okay, okay, this is the condition. So whenever we are increasing the VD more, then what happened, my channel is completely pinched off. Okay, it directly pinched off and it will move towards to the source side. Why? Because we are applying the, whenever we are applying the more voltage at the drain terminal, and because of that voltage my channel is moved away. Okay, so now what happened, here there is no conducting channel in between my source and drain. Why? Because my channel is pinched off away from the drain. Okay, now there is no channel. So even though we are increasing the VD, okay, even though we are increasing the VD, my ID current is constant. Okay, why? Because there is no channel, there is no channel in between source and drain, right? Why? Because my channel is pinched off. So even though we are increasing the VD, my ID current is constant. Okay, so which means constant means my ID current is saturated. Okay, so this is the thing. Channel pinch off appears near to the drain end, it appears, which means it moves away from the drain, and ID current becomes constant, which means constant or saturated. It is independent of VD, right? It is not depending on VD. Why? Because there is no channel, right? Even though we are increasing the VD or decreasing the VD, there is no change in the ID current, it becomes saturated. Okay, so it depends only on the VGS, right? So it depends only on this gate voltage. Why? Because there is no conducting path in between my source and drain. This current is known as ID saturated currents. Okay, so this is the thing. So some VI characteristics of MOSFET. So we can see some VI characteristics. Okay, so check here, we are constructing a graph, plot a graph between VD and ID. Okay, so what is in first case, in first case we are not giving any amount of VD, we are giving the VD amount as 0, which means here we are, at this case we are giving the VD voltage as 0. What happened at that time, my ID also 0, which means here this point is known as cutoff, right? Cutoff point, cutoff region, this is the cutoff region. Why? Because my VD is 0 and at the time my ID also 0, right? Whenever we are not applying any voltage, which means my VD voltage is equal to 0, there is no conduction of current in between source and drain, right? That's why ID also 0. So this is the cutoff region. So after that what happened, whenever we are starts increasing the VD voltage. So whenever we are increasing the VD, at that time what happened? My ID current is increasing. How it is increasing? It increasing linearly. See, check here. So whenever we are increasing the VD voltage, so see. So this is the VD voltages, right? So whenever we are increasing the VD, my ID also increases. Check here, right? It increases linearly, so that's why this region is known as linear region. Okay, it increases linearly with the VD, that's why it is known as linear region. So after that, here check here, we are increasing the VD voltages. So whenever we are starts increasing the VD voltage, okay, so what happening here, my ID current becomes saturated. See, check here, my ID current is now what happened? It will become saturated. So this region is known as, so this region is known as saturation region. Okay, so this is the case. So here cutoff, okay, here linear and here saturation conditions. So these are the four cases. Okay, understand? So cutoff region, linear region, and in this case we are not having any, we are having one conducting channel. So these all the cases are in depletion MOSFET. Okay, so in enhancement MOSFET there is no channel, but these are all the depletion MOSFETs, right? So in depletion MOSFET regions, whenever my VD voltage is zero, then we can observe cutoff regions. Whenever we are increasing the VD voltage, a small amount of VD voltage, okay, then we can see the current increases with linearly. After that we can see one pinch off region, okay, which means we are increasing the VD voltage is more than my threshold voltage. Okay, then we can see some pinch off regions or threshold regions. After that, whenever we are increasing the more threshold, more voltage more than my threshold, then what happened, my id current is become saturated. Why? Because there is no channel in between source and drain. Then my id is become independent of vd. Okay, even though we are increasing or decreasing, my id current is constant. Okay, these are the four operating conditions in MOSFET depletion type. Okay, so that's it for today's class. Okay, thank you.